Do one more example, and there's one in the slides, but I wanted to make up my own where I have this time a weak base with a strong acid instead of a strong base and weak acid. So basically the opposite. Now first of all, let's kind of graph this. Let's think about what's happening. Let me write this out. Here we are. Come on. 40 milliliters of 0.1 molar ammonia. So this is our weak base, okay? And this is going to be, put this over here. This is our analyte. Analyte, and I'm going to put weak base, okay? And then we're going to titrate this with 0.2 molar hydrochloric acid. And this is our titrant. Strong acid. So remember, the analyte, we always know the milliliters and the molarity. That's how I know that's the analyte. Okay, so let's kind of think about this in a graph form. Okay, we're starting off in our beaker initially with this analyte, NH3. Now this is a weak base, so what would the pH be? Would it be really high or really low? It'd be highish. Okay, so this is pH over here, and this is going to be milliliters of titrant that we add. Okay, so when we're at 0, let's say this is pH of 7. We're going to start off with, say, maybe like right here. Okay, why up there instead of down here? Because we have a weak base, so the pH is higher. Okay, so basically what will happen is we might have, and all of a sudden it's going to drop dramatically maybe right here and then head off. And so it's going to drop dramatically maybe right in here, right below pH of 7. Why below pH of 7? Because we have a strong acid. When we have a strong acid, that means your equilibrium pH is going to be right below 7 probably. And if you have a strong base, it'll be right above 7. But it'll never be 7 because we have a weak and a strong. Only with a strong acid and a strong base will it actually be 7. Okay, so we predict initially our pH is going to be high, and then it's going to go down a little bit lower, and then after equilibrium, or at equilibrium, it's going to go right below 7, and then after equilibrium, it's going to dramatically drop to way below 7. Okay, so let's set this up. Let's first find the initial pH. So let's find initial pH. Okay, let's do like all the different steps. Okay, or anytime you have initial pH for a weak and a strong, this is your ice table. Let's see, I'm just going to put weak analyte, and it really just depends if your analyte's an acid or a base. Weak analyte. Okay, so if we look here, our analyte is a base, so this is going to be a weak base problem in this case. Okay, so I'm going to have my NH3 plus water, just doing my equation for a weak base, and we're going to get NH4 plus OH minus. And this is just, from the chapter before, the same ice table for a weak base. Okay, so if I plug in all my numbers here, initially, and we're in an ice table like this, we put in our molarity. So initially my molarity for NH3 is 0.1. Water we don't care about. NH4 is 0 and 0. Our change is X, we don't know that. Plus X because these are products. Nope, that's the X. So then we're going to have 0.1 minus X, X, X. And let me give you the Ka equals to 5.6 times 10 to the negative 10. Now let's look at this. Since this is a weak base, we don't want a Ka, we want a Kb. So our Kb, then we just do 1 times 10 to the negative 14 divided by our Ka, which is 5.6 times 10 to the negative 10. So our KB equals to 1.8 times 10 to the negative 5. Now again, how did I know to use a KB versus a Ka? That's because initially our analyte is a weak base. So because we're looking at initial pH, because look, NH3 is our analyte. Okay, now if this would have been a weak acid, then I would have used Ka, but it was a base. So we plug this in, or we can get rid of this minus x. So when we plug it in, our products will be x times x. So I'm just going to go ahead and put x squared divided by 0.1, which is our reactant, equals to Kb. And we could plug that in further. So x squared equals to 0.1. And Kb we know is 1.8 times 10 to the negative 5. So solve for x. So 0.1 times 1.8 times 10 to the negative 5. So we're going to get x squared equals to 1.8 times 10 to the negative 6. Now remember, to get rid of an x squared, you raise it to the 1/2. Just to both sides, raise to the 1/2. So it gets rid of that. Because basically we get x, then if you did it correctly, will equal to approximately 0.001. Now what does x equal to? I mean, it equals to 0.001, but what do we care about? It equals to, right here, OH minus, hydroxide, okay? So this is our hydroxide concentration, OH minus. So from here we can get pH, okay? So if we do we get POH first. We know POH equals to negative log of our hydroxide. Because we can't directly plug this into the pH equation because this is OH, not H0 plus. So if we do this, we get POH equals to negative log of 0.001. And so when you plug that in, you should get POH equals to about 2.87. Okay, so then when we do pH, then, now this is a simple one, will just be 14 minus POH, which basically means pH equals to 14 minus 2.87. So pH equals to 11.13. Okay, so remember initially we said over here that we're going to have a pH, quite above 7, which is at 11.13. So our initial pH right here is about 11.13. Okay, so anytime you have an initial pH problem, you're just going to set up an ICE table just like you did before in the previous chapter. Okay, so now let's look at a before equivalence point. So when we do this, we need to know what the equivalence point is. Okay, so let's calculate equivalence point over on the side here. So we remember what that is. Okay, oops, no. And then let me see if I can drag this up. No. Still trying to figure out this whole thing here. Okay, let me just... hold on. Okay, sorry. Now I have this back. Let's do our equivalence point now. Equivalence point. Remember, that is going to be M1V1 equals to M2V2. So we have our molarity as 0.1. So 0.1 times our V1, which we have to put this in liters. That's going to be 0.04 liters. That's just dividing this by 1,000. So 0.04 liters equals to M2, which is 0.2 right here. 0.2, and we're trying to find volume 2, which is our equivalence point. So if we do 0.1 times 0.04, okay, and then divide that number by 0.2, we're going to get our equivalence point is, if you want 0.02 liters or 20 milliliters. Okay, so if I say what is the pH? pH at 10 milliliters, I know this is before equivalence point because the equivalence point is 20, so anything before 20 will be before equivalence point. Okay, so what do we do with this one? Let's think about what we're doing. So we have a before equivalence point problem. So this is a buffer. So we're going to be using the Henderson-Hasselbalch equation. So pH equals to pKa plus log of our base over our acid. Okay, so let's figure this out. Let's see. We know the Ka I gave to you just a minute ago is 5.6 times 10 to the negative 10. So then the pKa, remember, it will just be negative log of the Ka. Ka is 5.6 times 10 to the negative 10. So I plug this in. My pKa is, let's see, 9.25. Alright, so I know this part of the equation here. Now I need to get my base and my acid numbers, okay? So we're going to set up a buffer kind of table. And then when we do a buffer table, you put in moles. Equals to moles, okay? So how our analyte, so we need to know our analyte, how many initial moles? Initial moles analyte. So that when we get moles, or our moles will equal to molarity times volume. Okay, so our molarity times volume, initially, again, we have 0.04 liters times 0.1 molar. And I got this up here. Okay, that's what our initial things are. So initially we have 0.004 moles. Okay, now let's look at our titrant. Okay, how much titrant did we add? Okay, so let's see. We need to do moles. Moles equals molarity times volume. The molarity of our titrant is 0.2 right here. So 0.2, and what volume did we add? Right here is 10 milliliters, which is 0.01 liters. Oops. 0.01 liters. So I'm going to put in 0.01. So how much did we add? 0.002 moles. Okay, so we added this much titrant and we initially had this many analyte. Okay, so our change will be this right here. Okay, so let me put these again. So I have my analyte and my titrant. Oops, titrant. There we go, titrant. And initially, I had 0.004 moles just in the beaker initially before I added anything to it. And I had 0 of this. So this is before the problem even started. I had 0. Now my change, I just added 0.002 moles of the titrant. So I'm going to subtract that from the analyte and add it to the titrant. Okay, so when I do this, I'm going to get 0.002 and 0.002. And so my analyte, so let's see, I have here's my Henderson-Hasselbalch equation. Okay, which one is my base, my analyte or my titrant? That is my analyte, because I wrote it down as a weak base. So this is my base, which would make this my acid. So now let's plug everything in. I have pH equals to pKa, which I calculated is 9.25, plus log of my base moles, which I said was 0.02, over my acid moles, which is 0.002. So I'm going to plug all this in. So do 0.002, 0.0002 plus log, times log plus 9.25, you're going to get 9.25. Because this should just be 0 right here. So my pH equals to 9.25. Okay, so if we think on this, we started out, I think it was like around 11.13, so around 11. And now we've added 10 milliliters of a really strong acid, so now we're down to about 9.25. And we're at, after we added 10 milliliters. Okay, so maybe, let's see, we started about, right here. Now we're about right in here. Okay, so now let's do a equivalence point problem. Okay, so if I'm at equivalence point, okay, so I'm going to write on here. pH at equivalence point. Okay, so how many milliliters did I add? Because sometimes they won't tell you. You just have to kind of know. Well, I already calculated the equivalence point right here is 20 milliliters. So if they just say what's the pH at equivalence point, well, they assumed you already calculated it. So in this problem, it's going to be at 20 milliliters of titrant added. Okay, so for this one, for a weak acid, strong base type problem, so weak, strong, now all of your analyte, which is always your weak one, analyte, has changed, okay? So my analyte, okay, changed. It's the opposite. So if it was initially a weak base, that's what it was right here, a weak base, now it's fully converted into a weak acid at equivalence point because we've basically added enough acid to turn this into an acid. So basically, I hope that makes sense. So basically this has neutralized all of the acid that it can, and so it's turned itself into a weak acid. There's no more base left in the problem. Okay, so now we're going to do an ice table with a weak acid. Okay, we're at the beginning of the problem we did an ice table with a weak base. Now we do it with a weak acid. So one of the hardest parts is to remember to do that. So let's just put HA for a generic acid plus water gives us H3O plus A minus. Okay? And we have our ICE. Now the next hardest part is remember what do we put in here? Okay, so again, our molarity, we're going to put in molarity. Anytime we have an ice here, we put in molarity. You put in molarity in there. And if you have a Henderson-Hasselbalch equation, you put in moles. Okay, so put in molarity. Molarity equals 2 moles per liter. Well, our moles aren't going to change. So our initial moles, we had 0.04 liters times 0.1 molar. So that's just right here. I'm just defining initial moles where moles equals to molarity times volume. So my molarity initially was 0.01 and my volume initially was 0.04. So I'm just right there my analyte. So my initial moles was 0.004. Okay? But my liters have changed, right? In my beaker now, I don't just have 40 milliliters. I have 40 plus 20 because I've added 20 more. So I need to put that on there. So my new volume is going to be 0.04 plus the 0.02 that I added right here. Okay, so what is my new molarity? Okay, so I have 0.004 divided by 0.04 plus 0.02. I get about, let's see, equals to 0.067 molarity. So I'm going to put that right there. So that's the next hard thing to remember is this right here. You have to figure out your new initial molarity because it's not the initial molarity of the initial problem, okay, like we did in the other ice table, because now we've added more liters, we've added more volume, okay? So we had to compensate for this 20 milliliters we add to the beaker. Okay, so now we have this. Now everything else is the same, so this is simple. 0, 0, minus x plus x plus x, so that'd be x, x, and then 0.067 minus x. We can get rid of that x. Okay, now let's think. Do we use a Ka or a Kb? So we ask ourselves, well, is this an acid or a base? Well, now we're looking at a weak acid, so we need a Ka, which I gave you as, let's see, 5.6 times 10 to the negative 10. Okay, so now let's set up our Ka. We know our Ka equals to 5.6 times 10 to the negative 10 equals to our products, which are x times x, which would be x squared, over our reactants, which is 0.067. So let's solve for x. Okay, I have 5.6 times 10 to the negative 10 times 0.067. That gives me 3.75 times 10 to the negative 11 equals to x squared. Now to get rid of the squared, we're raising it to the 1/2. So I'm going to raise my answer to the parentheses 1/2 in parentheses. So x equals to, say, 6.12 times 10 to the negative 6. Okay, so let's look at this. So we have, what is x equal to? Basically, what do we care about? We would go back to our chart. In this case, we care about H3O plus. So x equals to H3O plus. Great, this makes it simple. So now we have H3O plus concentration. Now all we need is pH, so we do pH equals to negative log of H3O plus, which we know equals to 6.12 times 10 to the negative 6. Okay, so pH equals to 5.21, which I told you is going to be right below 7, so that's, right in here, 5.21. So at equivalence point, it's 5.21 is our pH. Again, anytime we have a at equivalence point problem, you're always going to have to do these steps. Your analyte will change either what it is. So in this case, it's a weak base, so it turned into weak acid. So you need a Ka, okay, and you need to find your new molarity. Okay, now let's do our last problem, which would be after equivalence point. Let me delete this. Now I think this one's the easiest because it's just like a strong acid, strong base. Okay, so after equivalence point, so if our equivalence point is 20, so let's say after 25 milliliters have been added. Okay, well, here's the formula. Right? You're going to do moles of your titrant minus moles of analyte divided by all of our volumes. So initially we had 40 milliliters, so I'm going to put, so our volume of our analyte plus the volume of our titrant. Okay, in this case, so this will either equal to H3O plus or hydroxide, depending if at this point we have an acid or a base. So whatever the titrant is, that's what it'll be. Because right now we have more titrant. Because we had a lot more analyte. Now we've added so much titrant, we've dripped so much in there that now we have more titrant. So what is our titrant? It is a acid. So in this case, it's going to equal to H3O plus. So let's put this in. So how many initial moles of titrant, or no, how many moles of titrant do we have now? Well, remember, moles equals to molarity times volume. Okay, so in this, we're going to do our titrant. Okay, so what is the molarity of our titrant? We have it over here as 0.2. And what volume have we added? Well, that's the 25 milliliters, or the 0.025 liters. Okay, so let's multiply this out. We have 0.2 times 0.025. 0.005 moles. Now let's do our analyte. We've actually already done this, our molarity times volume. Well, we have, because we haven't added more analyte, we've only added more titrant. So we have still the 0.1 molar times our volume, which is 0.04. That's all from right here, okay? So we do this, we're going to have 0.004 moles. Do you see, when we're looking at the titrant and analyte, see that we have 0.005 versus 0.04? So we have more moles of titrant. And that's how I know I had more moles of titrant, and we have, so this gives us H0 plus. Okay, now, so let's plug this in. So our moles of titrant is 0.005. Our moles of analyte are 0.004 divided by our volume of our analyte, or our analyte volume hasn't changed, so it's still 0.04. Plus the volume of our titrant, and right here our titrant we've added 25 milliliters, so that'd be 0.025. Okay, so let's plug all this in. So I have 0.005 minus 0.004, you put that in parentheses, divided by parentheses 0.04 plus 0.025 in parentheses, and I get 0.015. 0.015 molar, and what do we say this equals to? Or H3O plus. This equals to H3O plus, which is great. So now all we have to do is plug this into our pH equation. So pH equals to negative log of H3O plus, and our H3O plus is 0.015. So negative log of this answer, and I get pH is about 1.8. Okay, so now when I've added 25 milliliters of a really strong acid, my pH drops significantly from my equivalence point to right here. Okay, so at equivalence point, the pH was about 5. Okay, I added just 5 more milliliters of this acid, and it dropped all the way to 1.8, down to here. Okay, so I started off really basic, or I say pretty basic, and then by the end, the more acid I add, the lower the pH becomes. Okay, so I know this is a lot to take in, a lot of math and everything, but I posted, the little paper that kind of tells you to do at each point. So what I would do is, when you look at these problems, think, okay, is this an initial pH, before equivalence point, at equivalence point, or past equivalence point, and then from there think about what you do, okay? And the steps that you take are always going to be the same. The only thing that will change will be the numbers. So I hope this helps, and let me know if you need more problems.